Hi, I'm Peter Wei, here to give an update on the LASA InvenTeams flying drone. For those of you new to the program, let me introduce the concept of the invention. The invention is a system for evacuating tall buildings during emergencies by connecting cables between the building and its neighbors on as many sides and floors as practical. The cables are connected by a flying drone that pulls a lightweight tether across to the other building. The tether is used to reel in the cables across which the evacuees traverse to safety. The portion of the invention that we are prototyping is the automated drone. It consists of a quad, 4-bladed rotor helicopter powered by a 12-volt power supply and controlled by 2 microprocessors. With a built-in gyroscope for horizontal reference, it uses a combination of sonar and photosensors to track an optical guidance system to its target. Our goal is for the drone to be capable of takeoff, guidance tracking, flight, and landing. Now I will discuss our software development. Here in front of me is the controller board with an NXP2138 microcontroller. It can control 6 motors, has analog digital converters, timers, ARM CPU, and memory. We will employ 2 of these, one dedicated to motion control and the other to sensor signal processing. The software we use is Eclipse running on a Windows laptop, which connects through a USB cable to a JTAG interface to the controller board. The firmware for the microprocessors is written in a combination of assembly language for initialization and setup, and the rest in C programming language. We compile our C programs, then download it to the controllers where it is executed. This is a diagram of the architecture of the drone control system. In this animation, the 2 large squares in the center represent the 2 microcontrollers. The left one is for motion control. It controls the speed of the motors that drives the rotors. It also controls flaps for counterclockwise and clockwise yaw so that the drone can turn left or right. The right microcontroller reads the various optical and sonar sensors to feed position information to the motion controller. The 2 controllers act in unison, one as the eyes and ears and the other as the arms and legs. Our firmware is a real-time exec. Shown here is the flow diagram. On the left is the reset and initialization control path. We initialize the processor, memory, timers, A to D converters, and PWM units, or pulse width modulators. The PWM units control the motors. We start up the exec called main, and the exec sets the real-time execution intervals by programming one of the timers. We are using 1/50th of a second for these intervals. A processing cycle occurs 50 times a second, and all processing tasks must be completed within 1/50th of a second. At the start of our processing cycle, we program the timer to start the countdown to 0 and increment a global variable called index to set the modulus of the current processing cycle. High priority tasks are processed every cycle. Half priority tasks are processed every even cycle, the index is even, or every odd cycle, the index is odd. Quarter priority tasks are processed when the index is 4, the even 4th cycles, or 3, the odd 4th cycles. This structure lets us put high priority processing tasks in the section of the exec where they are performed every processing cycle. Half priority tasks can be put in the sections of the exec that execute every other processing cycle. Having even and odd versions of half-priority tasks allows us to spread the half-rate work across odd and even cycles. Quarter-priority tasks are tasks that only need to be processed at a rate of every 4 processing cycles. These can be spread evenly across the processing cycles as well. This makes every processing cycle perform about the same amount of tasks. Here is how we are allocating tasks to the different priority sections of the program. All system dynamics are processed with IIR, infinite impulse response filters, and this processing is high priority. Results of the system dynamics are motor speed settings and any mechanical actuator settings. Updates to hardware control is high priority. Calculating pitch, roll, and yaw angles and elevation are half priority. Motion control algorithms and telemetry transfer from the signal processing processor are quarter priority. The second processor will be dedicated to reading and processing signals. These include the gyro angle, sonar height, and directional scanner transducers. The motion processor and signal processor will communicate with each other over a serial bus called the SPI bus. They will have a mailbox and semaphore memory location to synchronize and perform handshaking of data to ensure that no data is lost, overwritten, or corrupted. Here you see the gyro in action. We used an old hard disk drive because it is precision balanced and can spin at speeds of 5,000 rotations per minute, which gives us plenty of angular momentum. The precession due to gravity aligns the spin axis to be vertical. As I tilt the drone, the 2 degrees of freedom gimbal remains horizontal. It is against the horizontal plane of the gimbal that the sensors will measure our pitch and roll angles. We are using Hall effect sensors and permanent magnets at the hinges of the gimbal to measure pitch and roll angles. As you can see, we have the drone powered and hovering while tethered down. The 4 quad-bladed rotors provide enough lift to hover at less than half throttle. We have had some setbacks with the motors overheating and failing. We think that the problem is in the stator wire insulation melting and causing the rotor phases to not synchronize. So far, the new motors have not exhibited the overheating. We think the airflow through the center of the motor is improved in these motors because the gaps are larger. The drone with motors weighs about 6 pounds total. We will do some more weight reductions by cutting out unneeded material the next time we have the motors detached.